Hello everyone, welcome to Your Code Galaxy. Today we will take a deep dive into the inner workings of a container technology. A short disclaimer. Before we begin, I would like to inform you that this is not a Docker tutorial. This is a deep dive into the container technology on which the Docker service is built on. I am working on a full-fledged Docker tutorial. Please subscribe to get updates when the Docker tutorial is released. But I would strongly encourage you to watch this video as it will give you a close look at how containers work on a fundamental level. Let's begin. The most common frustrating challenge in software today is the code lottery. The problem is framed in a joking manner as it works on my machine. What it means is when a programmer finishes their code, it runs perfectly on their personal computer. But as soon as they move it to the server, it suddenly stops working or behaves strangely. The reason behind this is your computer and the server are different. Your computer has specific versions of helper files, operating system settings, and tools that the code needs. The server has its own, often slightly different versions. The solution: containerization. Containerization solves this problem by taking the code and all its necessary ingredients, libraries, settings, etc., and putting them into one single sealed package. Think of it like a lunchbox. Instead of just sending a sandwich, that means the code, to the server and hoping the server has the right plate, napkin, and drink, you put the entire meal into a sealed, complete lunchbox. The container doesn't care what the server looks like. It always opens its perfect environment inside the sealed box, guaranteeing the code runs in the exact same way every time, everywhere. Here you can see the application works fine on the developer's local machine, but it fails to run on the server. The biggest culprit is the environmental drift, which means there are little natural differences that build up between the developer's computer and the server over time. Let's see what benefits the containerization provides. Containerization provides immutability and portability for your application. Let's talk about immutability first. Immutable simply means cannot be changed or fixed. And infrastructure in our context means the contents of the container, the libraries, OS, dependencies, etc. That means once your container is created, it cannot be changed. So how does it help us? Let's take a look. Once you build your container image, the contents of that image are locked in. Any two containers built from this image will always be exactly identical. This means once a developer is done with their coding part, they can build an image that capture the exact setup of their local computer and distribute this image. Applications running inside the containers built from that image will behave exactly the same way, the way they did on the developer's local computer. This ensures that you are running the exact same setup in development, testing, and production. Now, let's look at portability. Because an image carries the application and the dependencies, it becomes extremely easy to run your application absolutely anywhere. All you need is a container manager running in that environment. Everything else is taken care by the image and the container manager. Let's see how this works. Your container, as the name suggests, contains your application and everything your application needs to run. This makes running the application everywhere extremely easy. You can copy your image anywhere and the application will run exactly the same everywhere. You do not need to worry about setting up your environment, your system before running the application. Unlike virtual machines, containers do not rely upon guest OS. This significantly reduces the size of the containers, which allows us to pack more containers on a single system, which is also known as bin packing. Let's take a look. A virtual machine requires a full-fledged guest OS to function. This significantly adds to the operational overhead. On the other hand, containers do not need their own operating system to function. This reduces their size significantly and allows us to pack significantly more containers than VMs on a single system. VMs have their own operating system, kernel, and virtual hardware. Loading the kernel OS libraries for every virtual system consumes significant amount of memory. Containers, on the other hand, share the host kernel and host resources. They do not need individual kernels or OS libraries. This leads to significant less memory consumption per container, allowing us to fit more containers per host system. Let's take a look. A single system is able to host more containers than VMs. This leads to significant increase in the efficiency of hardware utilization. Another benefit the containers provide is agility. As we saw earlier, containers share the host OS and kernel. They do not need to have individual guest operating systems, kernel, and other libraries. This significantly reduces the startup time for each container. For the host OS, every container is just an application. Now, because the startup time is so low, containers are able to quickly respond to sudden spikes in traffic and add more containers. Let's take a look. Traditionally, a virtual machine would take minutes to start up and be functional. A container, on the other hand, is up and running in milliseconds to seconds. Because of this, we are quickly able to deploy more containers if there is a sudden spike in traffic. Containers are the center of a microservices architecture. Because of containerization, we are able to break down large monolithic applications into smaller manageable applications called microservices. Since each container carries its own environment, it is possible to have applications with conflicting dependencies running in the same system. That means containers are also polyglots. Monolithic applications were difficult to manage. Moreover, if one service inside the application failed, the entire application had to be restarted. Containerization made decoupling of services possible. Large monolithic applications are broken down into small, manageable, logical chunks. This allows for independent development of each service, since failure of one service doesn't lead to complete shutdown. Another benefit is you now do not need to develop your entire system in just one type of environment. You can have multi-language system. Auth service developed in Java while payment service developed in Python. You're not tied to any one language. Now, let's quickly look at the differences between virtual machines and containers. A VM is an entire virtual computer. It uses hypervisor to create a complete simulated set of hardware, a virtual CPU, virtual memory, virtual hard drive, etc., for a separate guest operating system. Because of this, it provides a hardware boundary and strong isolation from the host. Since a VM needs a full OS in addition to the host OS, This makes VMs very heavy. Often, the size of a VM goes up to gigabytes. Additionally, for every VM, the guest OS also needs to be fully loaded into the memory, due to which a VM easily takes minutes to fully start up. On the other hand, a container is a package that includes only the application and its dependencies. It shares the host OS and kernel with other containers. Instead of simulating hardware, it uses kernel features to create an isolated environment for application. This makes them much lighter and faster to start than virtual machines. But the isolation is at the OS level, not the hardware level. Since there is no overhead of an additional operating system, the size of the containers is very manageable, often in megabytes. And because every container only needs to load the application in the memory and not an entire operating system, it only takes a few seconds to fully start up. I have a separate video that explains in detail hypervisors and how they make virtualization possible. I highly recommend watching that video to understand how virtualization exactly works. I'll leave the link in the description. Let's talk about the security problem that containers have. As we already saw, containers share the kernel of the host OS, which makes them very efficient, but there is a small problem with that. In a system with virtual machines, hypervisors set hard boundaries between all the VMs and also the host system. If one or multiple VMs crash, rest of the VMs and the host are still safe. But in the case of containers, the kernel is shared with other containers and the host machine itself. This poses two problems. If one container messes with the kernel, the entire system, including the host, can shut down. This is called the kernel panic. The second problem is that one container can access the memory of another container because they both share the same kernel. This is called the kernel escape vulnerability. Let's see how it looks. As we can see, in a virtual machine system, when one VM crashes, the rest of the system remains unharmed because each VM has its own OS and kernel. There is a hard boundary between all the VMs and between the host machine. Containers, on the other hand, share the host kernel. So, if there is some issue with kernel for any reason, all the containers on the host system are at risk of collapse. There is also the risk of data vulnerability since everyone is using the same kernel to communicate with the hardware. So, how do we solve this problem? Let's look at the mitigation strategies taken to solve the two problems with containers. The first one is called seccomp. It is basically a way to limit the system calls that a container can make. This prevents a container from running commands that can put the entire system at risk. Second solution is to drop root or admin privileges of the users or threads outside the containers. We will see in a minute how this looks. And the third solution is mandatory access control or MAC. This sets hard limits on the capabilities of container, restricting its abilities to harm the system as a whole. Let's take a closer look. So, our first mitigation strategy is the seccomp. It essentially filters the system calls a container makes and only lets the allowed calls to go through. This way, we can ensure a container does not make any calls it is not supposed to. The second strategy is capability restriction. A user or thread can have root privileges or admin privileges inside a container, but the same user only has general privileges outside the container in the host system. This further limits a thread from making any harmful changes to the host system. And lastly, we have the Mac. This is a hard limit on the capabilities of a container when it comes to interacting with the shell kernel. Any operation that endangers other containers or the host system is outright denied. This is how we are able to maintain security in a shared kernel system. Let's talk about the history of containerization. The history of containerization begins with the introduction of Unix Chroot or change root in 1979. Let's see how that works. In a typical system, a process would have access to the complete file system. Chroot would limit access of a process to a limited section of the file system. This ensures the application cannot make changes in the areas it is not supposed to. The next major leap was in 2000s with the introduction of FreeBSD jails. In Chroot, you simply restricted the access of a process to a limited files. But in FreeBSD jails, you turned that bubble into a miniature system by adding its own file system, users, and networking. This was done to facilitate shared hosting. Let's see how it works. FreeBSD jail breaks down one large system into smaller miniature systems. Each system has its own file system, users, and networking IP and ports. It made shared hosting possible for a single host system. In 2004, Solaris zones were introduced, which was enterprise version of the miniature systems we saw in FreeBSD. Solaris zones introduced snapshotting, meaning you could now make copies of your miniature systems to be used elsewhere. Solaris zone also introduced resource boundaries, which mean a process cannot consume resources more than it is supposed to. Let's take a look. Solaris zone not only created miniature isolated systems, they also allowed setting of limits on the resources that each of those systems can consume. Moreover, you could also take snapshots of these systems and store in a repository to be run on another system. Now, let's take a look at the modern era. In 2006, Google created Cgroups to manage their massive workloads. This mainly allowed them to track and monitor the resource utilization by their containers. Each group had a hard resource limit. Along with that, it also became possible to monitor usage of resources. In 2008, Linux Containers was launched. This merged the Cgroups with Namespaces, which added the isolation factor of the Cgroups. With LXC, you now had the power of isolating environments while limiting their resource usage. This was a container in its true sense. And finally, in 2013, Docker was introduced. The biggest contribution was the simple API that Docker introduced, which removed the need for complex commands required to run LXC. They made container technology accessible to the masses. Although LXC was designed to be a lightweight VM, it felt like managing a full Linux server. You still had to worry about OS updates, init systems, and complex networking. It was a tool for system admins. Docker abstracted all that away with its simple API. It turned containers from an ops task into a developer tool. LXC required you to build your environments from scratch. If you wanted a Redis server, you had to spin up a container and install Redis manually. Docker created a centralized repository called Docker Hub. Suddenly, you could have a working best practice environment in seconds by just making simple API calls. It lowered the barrier to entry from days of configuration to seconds of downloading. And in 2015, OCI standardization was introduced. It ended the container wars, which prevented vendor lock-in. You no longer had to be loyal to just one container engine vendor. OCI created two specific standards: the image spec, what a container looks like on a disk, and the runtime spec, how to run it. This is what allowed tools like Podman, Kubernetes, and Builda to flourish. They could all use Docker images without actually needing Docker installed. It turned containers into universal Lego bricks that any tool could play with. Now it's time to see what makes a container tick. Let's begin. A container is a combination of three Linux kernel concepts. First one is the namespaces. The namespaces provide isolation by controlling what a process can see. Example, its own files and processes. Namespaces partition global system and resources to give each container its own view of the system. Let's take a closer look. Namespaces primarily provide isolation. The type of isolations are PID namespace, which gives the application the illusion that it is process ID 1, means it is the only process running in the system. Network namespace, which provides an isolated network stack. That means the container has its own IP, ports, and routing table. Mount namespace. This gives the container its own mount points and root file system. And UTS namespace, which isolates the container's host name. So here you can see how a process that is just one of many on the host system thinks it is the only one running inside the container. Next is network namespace, which gives container its own set of IPs, ports, and routing table. Mount namespace provides a container with its own file system. And UTS namespace isolates the host name and NIS domain name. It allows a container to have its own identifier, example web server 1, separate from the host system's host name. This is crucial for applications that rely on hostname for configuration or service discovery. Let's look at a quick demo on how namespace isolation works. Now let's look at a quick demo. Here I have a simple Python code written in Flask. In it I have different paths which do different tasks. The root path simply transmits the name of the PC in which it is running. The /stress path simply stresses the system by loading 200 megabytes of RAM. The /write path writes a file in the local directory with a current timestamp, and /read reads that file. If the file is not present, it simply puts out an error. Okay, so let's first run this code. I will type python app.py. Now my server is running. Let's fire up a Chrome tab, and here I will go to localhost 5000, and it is telling me that the PC that it is running in is Your Code Galaxy PC. Great. Now I have a Docker file from which I have created a Docker image. I will start a container. These are the old containers. I will delete those. and I will fire up a new container. In this I will give it 0 for randomly assigning the IP. And now I have the same Python app running inside a container. This is the port in which I will find it. I will click here, and as you can see, it's not giving the same name as Your Code Galaxy PC. See, the host name change. This is the UTS namespace in action. The container has no idea that it's on my laptop. It thinks it's a completely new server. Namespace also provide isolation on a more advanced level, like inter-process communication or IPC namespace. It isolates shared memory and message queues, preventing cross-container memory access. Next is user namespace. This is a critical security feature that maps user IDs, allowing a process thread to be root or admin inside the container, but a normal user outside. And time namespace. This provides the ability to use different system clocks, which is useful for testing time-based applications and bugs. Let's take a close look. Since containers share physical host memory, IPC namespace makes sure that one container isn't able to access memory being used by another container. Another critical security measure is the user namespace. A user or thread can have root or admin access inside the container, but outside it is just a normal user. And finally, the time namespace provides a container with its own clock. This way, you can run a container in a completely different time zone for testing time-based bugs. The next Linux kernel concept that makes container work are the Cgroups, or also known as control groups. They manage resource control, limiting what a process can use. Let's take a closer look. Cgroups are the police of processes. They control what a process can use and prevent the noisy neighbor problem. Let's see how they work. Cgroups set hard caps on resources like CPU and memory. They use CPU shares to give critical containers more CPU cycles. Cgroups also track resource usage metrics for billing and monitoring. Virtual machines were created with set allotment of resources from the beginning. These allotted resources cannot be accessed by other VMs. This also means resources allotted to a VM can go unused and therefore are wasted. This is not the case with containers. We do not allot resources to containers. They access and use resources as and how they need. But this also means containers can hog all the resources, leaving other containers starving. Cgroups set hard limit on resource usage for containers. This makes sure no one container hogs all the resources for itself. Cgroups also make sure critical containers get priority access to the CPU using CPU share. And finally, Cgroups track usage metrics, which is critical in billing and accounting. Let's take a quick look. Let's look at a quick demo to see how Cgroups works. Now, we will take a look at how Cgroups are able to limit resource allocation. Let's fire up the terminal, and now I will run this command. Here we are setting a hard boundary of 100 megabytes on our container. Let the container run. let's verify that our container is running. So localhost 5000. Okay, my container is up and running. And I will also like to check Docker stats. And we have our container running, which is limited to only 100 megabytes of strict usage. Let's see what happens when we try to use 200 megabytes. If you remember, in our code, we have a /stress parameter. In this path, what happens is our application tries to load 200 megabytes. We will see how Docker reacts to it. So I will add /stress and then enter. And there you have it. The container dies instantly. The Cgroup saw that the container is trying to grab 200 megabytes when I only gave it 100 megabytes, and the kernel killed it to save the host. This prevents the noisy neighbor issue that containers might pose. The Linux kernel is transitioning to a unified hierarchy in V2. This transition moves towards a unified hierarchy of resource management. Cgroups V2 aims to simplify and improve upon the control mechanisms of the older Cgroups of V1. And the last Linux kernel concept behind functioning of a container is the Union file system that handles storage through an efficient layered file system for the container image. The Union file system handles container storage by creating an efficient layered file system for the images. Let's take a closer look. UnionFS allows stacking directories to create one single cohesive view of the file system. The structure of the file system contains layers. Image layers are read-only slices of the operating system and application. The container layer is a thin, writable layer placed on top of the image layers. Let's take a closer look. The UnionFS stacks their directories in layers. The OS and application sit in the bottom layer, which is a read-only layer. Any write operations are only done in the top layer called the container layer. Now, let's make a quick change to our code. In this, I will just add test and save it. And now, I will rebuild the image. So, I will write docker build -t, that is the tag demo app, and then dot. Press enter. Let's give it a few seconds. Now, do you see these cached entries? Docker did not download the OS. It only rebuilt the one tiny layer I changed. This is the efficiency we talked about. The copy on write mechanism. This is how UnionFS handles file operations efficiently. There are three operations in copy on write mechanism: reading, writing or modifying, and deleting. Let's see how this works. The entire file system is viewed from top to bottom. If a write operation is to be performed on a file, that file is first searched in the top writable layer of the file system. If the file is in the read-only area, at the bottom of the stack, it is copied on the top and a write operation is performed on it. A whiteout file is placed in the upper layer to mask the original file present in the lower read-only layer, so that from the next time only the latest updated file is referred and the old file in the bottom is ignored. Let's do a quick demo to see how copy on write works. Now, let's look at how UnionFS works. First, I will fire up a terminal. Let's make sure that we don't have any other containers running. Okay, there is one container running. Okay, it's not. Okay, good. Now, what I'm going to do is, I will run a command, then press enter. Okay, we have a Docker container running. We will go back to our Chrome window. Over here, I will type localhost 5000, and as we know it, this application is running inside the container. Now, if I write /write and hit enter, it says file written. Good. Let's read the file. Now, I do read. Okay, it's reading the timestamp. Good. Now, I will go ahead and kill the container. To do that, I will run the command docker remove. Okay, we have now killed the container. Let's restart the container. And the container is up, as you can see. Now we will go back to our Chrome tab, and here I will directly hit read because we already created the file, remember? Oh. The file is gone. Why? Because I wrote to the upper directory, the writable layer. When the container died, that layer evaporated, and only the underlying image remains in pristine condition. The overlay file system. The overlay FS architecture is a common implementation of the Union file system. Its key structure components are lower directory, upper directory, merged view, and the work directory. Let's see how it works. This is a simple representation of how overlay FS architecture looks. The lower directory holds image layers which are read-only. The upper directory holds the container layer which is read and write. The merged view is the unified view of the file system exposed to the container. The work directory is the kernel's internal scratch space. The OCI image specification. The OCI image specification standardizes what a container image looks like on disk. Standardization allows images to run on different tools like Docker, Podman, and Kubernetes. Let's take a closer look. The OCI image specification breaks down a container image into 4 parts. First one is the manifest. A JSON file describing the image. It lists the layer and the configuration. Second is the image index. A fat manifest that points to different manifests for different architectures. Example, AMD 64 or ARM 64. Config blob. Blob stands for binary large object. A JSON blob containing metadata like environment variables, entry points, commands, user settings, etc. And finally, at the bottom, we have layers, the actual file system change sets, usually stored as gzipped tarballs. Now, let's take a closer look at Docker architecture. The Docker architecture is split between a client and a server, also known as a daemon. The Docker CLI or the client is the user interface used to issue commands. Docker D, also known as Daemon, is the server. It is the background service that manages high-level resources like images, networks, and volumes. And container D is the component that the daemon offloads the actual container execution to. Let's take a closer look. The Docker CLI is the API interface that lets the user manage and operate containers. Docker CLI sends the command to Docker daemon, which is the background service that manages high-level resources like images, networks, and volumes. The daemon offloads the actual container execution to container D. Now, let's look at the chain of command inside Docker. Container D is the manager. It pulls images, manages storage. It passes the execution to the next component. Runc is the executor. It is the low-level tool that sets up kernel primitives like namespaces and Cgroups. It exits once the container process starts. Shim is the supervisor that stays alive to supervise the running container, managing its I/O and handling processes, which allows the Docker daemon to restart without interrupting the container. Let's take a closer look. The container D pulls the image and passes the execution to Runc. Runc talks to the kernel to set up namespaces and Cgroups and exits as soon as the container is up and running. The shim continuously monitors and supervises the running container. Every container follows the same steps for being operational. These steps are the life cycle of a container. Let's take a look at the 7 steps in the life cycle of a container. First one is the user action. User types docker run, which hits the API. Second is the daemon request. Docker D asks container D to start. Third is the config creation. Container D creates a config.json as per the OCI runtime spec. In the execution call, container D makes the runc create command. The 5th step is the kernel setup. Runc talks to the kernel to create namespaces, apply Cgroups, and then pivot the root. The next step is the process start. The application process starts and Runc exits. And finally, supervision. Container shim takes over to supervise the running container. Last demo. Now, let's see the runtime hierarchy in containers. First, let's start up a container. To do that, I will run the command okay. We have the container running and this is my container ID. I will copy it. This becomes tricky. Okay, and I'm pasting it in a different command. And now what we are trying to do is we are trying to pull the process ID for this container. Let's see. Okay, the process ID is 802, which we have saved in PID variable. And now I will run the command okay. Ladies and gentlemen, we got him. Look at the process output. We are tunneling into the Linux VM here. We see the container D shim binary running. See that flag -namespace mobi? That is Docker's internal signature. and right next to it is the container ID starting with 7F93. This process is the supervisor I showed you on the architecture diagram. Its entire job is to keep the standard in and standard out streams open and report back the exit code, allowing the main Docker daemon to restart without killing my application. This shows us that Docker is just a manager. Look at the process tree. Containerd handed this off to the shim. This shows the runtime hierarchy that we saw. Conclusion. According to the Cloud Native Computing Foundation, a container is a standard unit of software that packages code and all its dependencies so the application runs quickly and reliably from one computing environment to another. Let's look beyond this definition. We have spent the last few minutes looking under the hood at kernels, system calls, but I want to zoom out and show you why this matters. This isn't just a tool for startups or hobbyists. The entire modern digital economy is running on the engine we just built. In finance, when you swipe your credit card, that transaction is likely processed by a microservice in a container, isolated for security. In entertainment, when you hit play on Netflix or YouTube, that stream is being served by a container that's spun up in milliseconds just for you. In AI, those massive LLMs like ChatGPT, they are trained and deployed on fleets of containers to maximize GPU utilization. You remember bin packing? We moved from physical servers to virtual machines and now to containers. It is the hidden backbone of the internet. Efficient, portable, and invisible. And now you know exactly how it works. I hope you enjoyed this video. Please feel free to post your questions in the comment section. And if you like this video, please subscribe for more interesting technological videos. Thank you for watching. Have a good day.